Hello everyone, myself Srivalli, working as an assistant professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. In the previous session, we have discussed about what is a statement, what are the types of the statements, what are the truth tables for the connectives, and we have also seen how to construct the truth tables, and we have seen some word examples regarding all the 5 connectives, and we have also seen what is contradiction, tautology and contingency. So today, the overview of my presentation includes other connectives, truth tables, converse, inverse and counterpositive, syntax, semantics, well-formed formula, and also validity and satisfiability. So first let us understand what is the first one, other connectives. So in the previous session, we have discussed 5 basic connectives. Those are negation, conjunction, disjunction, implication and also by implication. And we have seen some truth tables also, how to construct the truth tables. So along with that 5 connectives, we also have other 3 connectives, and those are called exclusive OR, NAND, and the last one is NOR. So let us see one by one along with the truth tables. So here the first one is exclusive OR. So what is meant by this exclusive OR? Exclusive OR or exclusive disjunction. So here the other name for exclusive OR is exclusive disjunction. So it is a logical operation that outputs true only when inputs differ. So here that is one is true and the other is false. So that means here, so this resultant will get true when we have one is true and the other one is false. So it is not only we should have true and false, we can also have false and true also. Means the combination of true and false, the resultant will get true here. So here exclusive OR is denoted by OR with hyphen here or a plus with circle. We can also denote this exclusive OR plus with circle, or we can also write it as here OR with down hyphen. So let us suppose we have 2 propositions P and Q. The exclusive OR of P and Q will write it as here P exclusive OR Q. So we can use any symbol. So here it is not mandatory that you have to use only plus with circle, or you can also use this OR with hyphen. So here if you consider any 2 statements P comma Q, the exclusive OR of P comma Q is denoted by P exclusive OR Q. This is symbolical representation of exclusive OR. So let us see the truth table. So let us suppose here we have 2 statements P and Q. So as we have 2 statements here, how many combinations we will get here? Total 4 combinations. And the exclusive OR of P and Q, if you observe here, so here if we observe, when both the statements are true here, we are getting false. If one is true and the other one is false, we are getting true. And the same thing here, it is repeating, we also get here true. And if you have both the statements false here, we are getting false. So that means what is the condition of this exclusive OR here? In the previous slide itself, we got here, if one is true and the other is false, the output here you will get as true. So here if you observe, so when the combination you have true and false, the resultant you are getting true, otherwise you are getting false. So if you observe here, if you carefully observe, in the previous connectors we have biconditional. So the condition for the biconditional is, if both the statements are same, then the resultant output you will get as true. That means whenever you have true and true, the output you will get as here true, otherwise false. So here the output means here not only true and true, even if you have false and false also, you will get the resultant as true. So if both the statements are same, the resultant you will get as true, otherwise false. That is the condition for here biconditional. So the exact opposite of the biconditional is here exclusive OR. If both the statements are same, the resultant output is false, otherwise it is true. This is the condition here to construct the truth table for exclusive OR. Next we have NAND. What is meant by NAND? So here symbolically we will represent this NAND as with up arrow. So it is represented by up arrow. NAND is a combination of NOT and AND. So here we already know what is NOT, which is nothing but here this is negation, and AND is conjunction. So this NAND we will get from the combination of negation and conjunction. So if P and Q are two statements here, then we will denote this NAND as P, the symbolical representation of NAND, Q. So this is P NAND Q. And let us see the truth table here. So if you here observe, we have P statement, Q statement, and this is P NAND Q. So here we have the four combinations as we have the two statements here. Next we have, this is the resultant of the P NAND Q. So how you are getting this P NAND Q here? So what we have in the previous slide, if NAND is a combination of NOT and AND. So what is a NOT here? Negation. Means whenever you have the true statement, the negative of the statement will get the resultant. That is, if you have true statement, you will get the false. If you have the false statement, you will get the true. And what is the rule for construction of the truth table? AND. So if both the statements, if you have, for example, see, AND statement we have. How to construct the truth table for AND is, let us suppose here we have true and false. Let us suppose we have true and true, false and false, and let us suppose we have false and true. So what is the rule for this construction of the truth table AND is, even if one statement is false, the resultant value you will get false. So that is here in the last row and the first row you will get the false. In the remaining cases you will get, even in the third case also you will get false here. In the second case you will get true. Why? Because even if one statement is false, the resultant truth value will become false, otherwise it is true. So this is a condition of here conjunction. We have already seen the truth table construction in the previous session. Now, what is a truth table for NAND here? So NOT and AND means applying negation for the conjunction will get the NAND here. So that means after P and Q, first of all you need to do P and Q. So here after writing this P and Q columns, so here you need to write down what is P and Q values, resultant values. Then applying negation for the P and Q, you will get here P NAND Q. So here, so if you observe here, true and true, you will get true. True and false, you will get false. Why? Because the condition of the truth table of AND is, even if one statement is false, the resultant value will become false. So here, false and true, you will get false. False and false also, you will get false. Now, applying negation for this P and Q. So if you apply negation for this, true will become false. False will become true, and here also false will become true. In the last row also false will become true. So here this is the P NAND Q. So but basically whenever they ask a question, here you are not supposed to mention this P and Q specifically in the table, but you have to imagine in your brain and you have to calculate only P NAND Q. So this is NAND. So next we have NOR. What is meant by NOR? So symbolically here we will represent this NOR as down arrow. It is exact opposite of OR, means the combination of NOT and OR. So let's suppose here we have P and Q two statements. So then it is denoted by P NOR Q. Symbolical representation of NOR is down arrow. So let us see the truth table here. So here we have P, Q, two variables, and we have four combinations. And P NOR Q. So first, as just like NAND here also you are going to do P or Q. So what is the condition for construction of the truth table for OR is, even if one statement is true, the resultant truth value will become true, otherwise false. So in the first three cases, first rows, here you will get here. So P or Q you are writing here. So in the first three cases you will get true here, and otherwise you will get false. Now applying negation for this P or Q, you will get the resultant value of NOR. So here negation of true is false, true is false, true is false, and here false will become true. So this is the construction of the truth table for NOR. So next we are having converse, inverse and contrapositive. So here if you observe this converse, inverse and contrapositive, we have three statements. So basically these are the three conditional statements where we will get from the conditional statement. So in the previous session we have discussed about what is a conditional statement. So here conditional statement means if P then Q. Symbolically we will represent it as implies. P implies Q. So here if you have any question here, for example if you are taking any question, if you work hard then you will pass the exam. So that is P statement is you work hard, pass the exam is Q statement. And if you apply if then here, if you work hard then you will pass the exam. That is like you will form the conditional statements that we have already seen in the last session. Now from this conditional statement we can form three new conditional statements and those are called converse, inverse and contrapositive. So here, so basically in this P implies Q, first P we can call it as, this P is called as antecedent and Q is called consequent. So what is meant by this antecedent and consequent here? Antecedent is nothing but the statement which is reaching to the conclusion. From the statement which is reaching to the conclusion here, antecedent means the first part will call it as, before implies whatever you have, that first part will call it as antecedent and the second part means after implies whatever the statement you have, that is called consequent. So if P then Q means before then you have P statement which is called antecedent here and after then you have the Q statement which is called consequent. And the other name for antecedent and consequent is hypothesis and conclusion. This is hypothesis and conclusion. The other names for antecedent and consequent are hypothesis and conclusion. So here, if you observe here, what is meant by this converse? What is meant by this inverse and contrapositive? So let us see here carefully. If you interchange the antecedent and consequent, then you will form a new conditional statement that is called converse of the original statement. So basically here, what does P implies Q here? This is a conditional statement. From this we are getting this converse, inverse and contrapositive. So what is converse here? Interchanging antecedent and consequent. Here what is antecedent here? P. What is consequent here? Q. So then if you interchange these two, then P implies Q here we have, if you write here Q implies P, then it is called converse. And what is inverse here? Negating both antecedent and consequent from the, that is called the inverse of the given statement. Means applying negation for the conditional statement. So here negation P implies negation Q. Next we have contrapositive here. What is this contrapositive? Interchanging and negating both antecedent and consequent, then you will form the contrapositive. So here applying negation for the converse. That is called, what is converse here? Q implies P. Applying negation means here negation Q implies negation P. So here if you observe the table here, we have conditional, converse, inverse and contrapositive. So this is P implies Q. Converse is applying here, interchanging between conditional statements. That is just interchanging P and Q statements. Inverse is applying negation for the conditional statement. Negation P implies negation Q. And applying negation for the converse is called contrapositive. Inverse, you can write here if P then Q or if Q then P. And here if not then not Q. If not Q then not P. So these are the four statements we are having: converse, inverse and contrapositive. Along with this, conditional statement is also there. So that's why we have altogether 4 statements. The other 3 are derived from the first conditional statement. So next, let us see one word example, how to convert the conditional statement from converse, inverse and contrapositive. So here let us suppose here as we have to get the conditional statement here, we are writing directly, if water is frozen, then its temperature is below 0 degrees centigrade. This is a conditional statement here, as we have here if and then. So P statement is water is frozen, Q statement is temperature is below 0 degrees centigrade. Now, what is meant by converse? Converse is here, let us suppose this is conditional statement, P implies Q, then converse will become Q implies P. Means exchanging hypothesis and conclusion. Here, the other name for antecedent and consequent are hypothesis and conclusion. We are just interchanging P and Q statements. So, then what is the converse? It will become in the word example. If the water temperature is below 0 degrees centigrade, then it is frozen. So, here we have just interchanged. This Q has came here and P has came here. Just we have interchanged P and Q statements. Next, inverse. Negating both hypothesis and conclusion. So here, just applying negation for this first statement. If the water is not frozen, then its temperature is not below 0 degrees centigrade. Next, the third one is contrapositive. Negating both hypothesis and conclusion of the converse. Means applying negation for the converse. Means for the statement we are writing not. If the water temperature is not below 0 degrees centigrade, then it is not frozen here. So this is the converse, inverse and contrapositive word examples. So next we have syntax of the propositional logic. So what is meant by syntax? So basically we know the general meaning of the syntax is here structure. So structure of the propositional logic. Not only for propositional logic we have the structure. If you consider C programming, we have the structure. If you consider Python, we'll have the structure for Python specifically. And if you consider Java, even for Java also we have structure. So structure means what? What is meant by a structure? The general meaning of the structure is here some set of rules and regulations to follow that particular language, whether it is C programming or Java or Python or even a propositional logic also. Some set of rules or some set of grammatical rules to follow to write the statements in propositional logic in our language. So here, if you want to write any statement, if you want to write any formula, first you need to follow some structure. So for our propositional logic, so here we need to follow some rules and regulations. So those are using logical connectives and operators which connect or operate on propositions. Means you need to follow some logical connectives and operators, and you need to use some symbols also, and you need to use some letters also if you want to get some statement or Wolfram formula. So here we need to get some letters also, and we have to use operators also. That operators can be either binary operators or unary operators. So here unary operators are nothing but we have only one unary operator which is called as negation, and binary operators we have here implication, by implication, and even we have here this is conjunction, and also we have or. So, and not only these operators, we can also specify the brackets, that is grouping the symbols. So, the combination of all this will become here a statement formula. Means here these are only some set of rules to get the statement formula. But if you use this in a meaningful way, that is called semantics. So, here syntax is nothing but only the structure to follow, the grammatical rules you need to follow, or some set of rules you have to follow for the propositional logic. But if you are applying that in a meaningful way, that will become as a semantics. So here propositional logic, it gets its meaning by being interpreted. Means here this meaning will be get by being involved in that propositional logic. So first let us understand. Before going for the interpretation, first understand what is a function. A function is nothing but a specific kind of relationship between two group of things. So here we are going to apply a function between two group of things. So the first group of things is called domain, or we can also call this as inputs. And the second group of things is also known as here range, which we can also call it as here outputs or values. So the function between these inputs and outputs is such that here for every input you will have only one output. So this is inputs and outputs relation. So the semantic of the propositional logic, it involves two important functions, and those are called interpretation function and the other one is valuation function. So what is this interpretation? What is this valuation function? So interpretation is nothing but, in short, we can say that this is called possible combinations, assigning truth values to the propositional letters. And valuation means what? Assigning truth values to the statement formulas, well-formed formulas is called valuation. So let us consider one example. There I'll explain what is interpretation and what is called valuation function. So let us suppose we have conjunction. So for the conjunction, we should have two variables, P comma Q. And here we should have P and Q. Symbolical representation is P and Q. So as we have two variables, here you will get the four combinations: true, 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 false, false, true, and also false, false. These are the four possible combinations. And what is the condition here for the construction of the truth table is, even if one statement is false, the truth value, the resultant value, you will get false, otherwise true. So this we already know as we have constructed the truth table in the previous sessions and even in this also. But what we can say interpretation in this, what is valuation? So here interpretation is nothing but the possible combinations of the propositional letters. It takes propositional letters as inputs and assign truth values to these propositional letters. Means here I of P is equal to true, I of Q is equal to true. So that means it will just assign the possible combinations for the propositional letters. Only for the propositional letters it will assign the truth values. So this is I of P is equal to 2 and I of Q is equal to true. And what is P and Q here? P and Q is nothing but valuation. Assigning the truth values to the valuation, that is statement formula. That is called valuation function here. So now how you will write here this I of P, I of Q and valuation is, this valuation of P and Q will become true if I of P is equal to true and I of Q is equal to true. So this applying the truth values to the well-formed formula, the statement formula is called valuation function. Means this is giving some meaning to this statement formula. If you consider individually here, I of P is equal to 2, I of Q is equal to 2. Just it is giving the values here. We are giving just truth values to this propositional letter. But when will it get meaning here? When the statement formula assign truth value. Based on what here? The valuation of P and Q will become true if I of P is equal to true and I of Q is equal to true. So not only this, you can also write for the other cases, other rows also here. I of T is equal to, here valuation of P and Q will become false if I of P is equal to true and I of Q is equal to false. Not only in this particular situation it is becoming false, even for the other two rows also it is becoming false. So that means you are writing this with the pronunciation of interpretation and valuation. Interpretation is the possible combinations, valuation is nothing but here you are giving some meaning to that statement formula. So this is about semantics of the propositional logic. Next we are having well-formed formula. So here we can say simply the statement well-formed formula is called the combination of syntax and semantics. Means following all the syntax of the propositional logic in a meaningful way, then we'll get the well-formed formula. So here if you observe every statement A to Z, the variables whatever you are considering, it is called a well-formed formula. If P and Q are well-formed formulas, then negation P is called a well-formed formula. Why? Because it is following the syntax of the propositional logic and it is having the applying the truth values also for this. That's why it is called a well-formed formula. P and Q is also called well-formed formula. P or Q, P implies Q, P by implies Q. These are all called well-formed formulas as we are using all the rules and regulations of the syntax, that is propositional logic, and also we are using it in a meaningful manner. That's why it is called well-formed formula. And nothing is a well-formed formula unless rules 1 and 2 imply. Means if you are not using these letters or if you are not using this in a proper manner with these connectors, this is not a well-formed formula. So let us see which are not well-formed formulas also. Here strings which are not well-formed formula. So if I write here P negation Q, so this is not a well-formed formula. Why? Because here we don't have any connective between P and Q. Why? Because here we have two variables. So for the two variables you need to use binary operator. We don't have here binary operator. We have only unary operator, that too only for Q here. So as we have two variables, you need to use binary operator. So that is missing here. That's why it is not a well-formed formula. And not only this, so if you see the second statement here, and QP. So you have to use it in a meaningful manner. As here if you observe, we are using the syntax of the propositional logic. That is, we have the letters and we have the connectivity, and the connective operator also binary operator, as we have two variables. But we are not using it in a right manner. It means we don't have any meaning for this. We have only syntax. That's why it is not a well-formed formula. Even if you observe the third one, so here we have implication R. So here, as we have the binary operator, we should have two operators, two operands here, but we have only R. We don't have other connective here, operator. So that's why this is not a well-formed formula. So strings which are well-formed formula here, so P and Q. So as we have P and Q here, we need to group the symbol, and next we have the by implication symbol, next we have R. So this is called a well-formed formula. And negation of X or Y implies Z is also a well-formed formula. So here, for this P and Q, you need to give the brackets. Otherwise, if you are not giving any brackets here, the meaning will be changed here. P and Q by implies R if I write without grouping the symbol. So here this Q will be given, first it will be calculated with R, by implication R, then it can be calculated with P also. Means here we should not follow this one. So here we need to group the symbol. Why? Because we don't have any clarity here. So that's why grouping the symbols also is very important. That's why it is also considered as one of the structure of the propositional logic. So we need to use the letters or variables. You need to use the operators, and also you need to use the grouping of the symbols. So together only if it is adding meaning, that's why it is called well-formed formula. So by this well-formed formula is done. Next, we have validity and satisfiability. So what is meant by this validity and satisfiability? First, let us see the validity here. A formula is valid if it is true for all values of its terms. So here, that is nothing but a statement formula is said to be valid if it is necessarily true under all possible situations. So this is also called it as here tautology. So here a statement formula is said to be validity if it is true in all possible situations. Means here if you have truths in all possible situations, then we can say this is called validity. So basically it is also called it as tautology when you are constructing the truth table. But formally you can write it as here, this is a validity. Satisfiability refers to the existence of a combination of values to make the expression true. So in short, we can write a proposition is satisfiable if there is at least one true result in its truth table. Valid if all the values it returns in the truth table are true. So that is nothing but here satisfiability is nothing but if it is true in some cases and if it is false in some other cases. Combination of truths and false is called this satisfiability. We can also write this satisfiability as contingency in the construction of the truth table. So here this is validity and this is called satisfiability. So by this we'll end the session, and we have discussed today, what we have discussed is So today we have discussed what are other connectives, that is NAND, NOR and also exclusive OR, and we have seen the truth tables to construct all this three connectives, other connectives, and we have also seen converse, inverse and counterpositive, and the word example how to convert that converse, inverse and counterpositive, and we have also seen here syntax, semantics, well-formed formula, validity and satisfiability. In the next session, we'll discuss about what is logical equivalence, how to implement that logical equivalence by using two representations. So by this, we'll end the session. Thank you.